Welcome, everyone. It's my pleasure to introduce Iván, who's going to be talking about contragredient Lie algebras in symmetric tensor categories. Feel free to start whenever you're ready.
Okay. Thank you for the invitation. It's a big pleasure to give this talk in your seminar. Thanks, Florencia, especially. We meet again, at least virtually. Let's hope to meet soon in person. What I want to talk about today is some work. A joint work with Julia Plavnik and Guillermo Samarco, two other people from FAMAF here in Córdoba, but now in US. The first one is about semi-simplification of contragredient Lie algebras. And the second one is about how to introduce the notion of contragredient Lie algebras in symmetric tensor categories. Here you have Julia, Guillermo, and also Hector in this photo. And this is funny because this is a picture in Hamburg because we met there and we made a good progress of our work there. So it's funny to have this picture there. Okay. This is about symmetric tensor categories. So first, I would like to introduce what I mean by symmetric tensor categories. When you talk about tensor categories, sometimes you mean that they are k-linear or not, and so on. Sometimes some people call tensor what it's monoidal or monoidal but it's tensor, so it's better to fix what I want to talk about. And what I mean by a symmetric tensor category is a category which is abelian. We want to have kernel, co-kernel to add objects, maps, and so on. K-linear, so we want that the home spaces are k-vector spaces. I'm not going to define precisely what it is, each one of these notions, but the main points about them. Then we want a monoidal category because we want to have tensor products between objects and maps. And in that sense, I want that the tensor product is k-linear. This is the compatibility between the k-linear category and the monoidal category that I want. We want a unit. This is related with the monoidal structure. Some objects such that when you tensor with it, you don't change the object. Essentially, you have an isomorphism. This is the meaning, which is associative, this tensor product. In addition, we ask for the endomorphism of the unit object to be just the field where we are working with, a fixed K field. In most places, it will be of positive characteristic, but essentially, the first part you can define over any field. This is fine. And I want also to have duals. So I want for this category to be rigid. This is the other thing that I want. So essentially, we can start thinking on vector spaces, but finite dimensional vector spaces, because we want to have duals with a nice property. And we want also to have a braiding Z, but in this case, I want to be symmetric. So it means that we have a way to exchange objects in such a way that when you exchange twice, you do nothing. Essentially, this is what you do. And the last thing is, if to this category we add an extra condition, we will have a Petranakian category. What it is? As we have kernel co-kernels, we can talk about exact sequence. We can talk about simple objects, intercomposable objects, and so on. But about simple, once you have simple objects, you can talk about Jordan-Helder theorem, and then you talk about length. In the same way that you talk about length for modules. And what you want is to have finite lengths. It means that every object can be written as an exact sequence with finite objects, essentially, which are simple ones. Iteratively, let me say. So what are the main source of symmetric tensor categories? Representations of a group. Finite dimensional representations, because we want dual. Essentially, what we want is to have a unit object, which is the field, the trivial representation. We know that if we tensor with the trivial representation on one side or the other, we get an isomorphism with the initial representation that we have. If we have two representations, then the tensor product is again a representation where you act on each side of the tensor product. And the dual is also a G module because you act by the inverse inside, let me say. This is some things that you can now in the advanced algebra course. And in this case, we can take the usual flip to exchange the two parts. And then this is a map in your category, which is natural in the sense that you can compose with with morphisms of G modules. And this is a kind of transposition that we want. When we do twice, we get the identity. This is fine. And I say here a group, and I don't say so much. In principle, you can think on a finite or discrete group, let me say, but you can think also on an algebraic group. And in this case, essentially what we have is the comodules over a commutative of algebras. I'm not going to say so much, but for those that know what is an algebraic group, this is what the other source that we can have here. And there is a third source of examples which come from Lie algebras. Suppose that you have a Lie algebra, you know that what it is, or if you don't know what it is, a G module, essentially what you want is to have an action in the same way as an action as usual. And the compatibility is the way to realize what you do with the bracket. Essentially, we know that if we have an associative algebra, a way to produce a Lie algebra is to put the usual bracket using the multiplication. So you reproduce this for the action, essentially is what you do. Sorry?
Oh no, I think someone didn't have their mic muted. That's what happened.
Okay.
Yeah.
And
Thanks.
we fix a finite dimensional G modulus by the same reason that we want for duals. We know that the tensor product of two G modules is again a G module, in which way this is a kind of derivation. You act in the first part, plus you act in the second part. We have a trivial representation, which is the action by 0, essentially. And we know that we have this dual isomorphism of G modules when we tensor with this trivial representation. Oh, this one is, okay, I don't know why. And the last one is that the usual flip is again a morphism of G modules, which is okay. You can check this thing. What happens with all these examples that I show here, essentially that they are vector spaces plus an extra thing, but maybe we want something which is not essentially the main change that I want to do is to change the symmetry that we have here. What is the simple example when you can have this? Essentially, we can take super vector spaces. It means that we take set two graded vector spaces, so we have an odd part and an even part. The tensor product is in the way that you multiply numbers. To have an even part, you multiply two even numbers or two odd numbers. And to have something which is odd, sorry, here, it should be a tensor product here, and here. I made that mistake. To obtain an odd number, you multiply an odd number by an even one. This is the way in which you have this rule. The unit is the field, but placed in degree 0, let me say. This is the meaning of this case 0. And for the symmetry, you exchange things, but in a different way than the usual one. If you have two things which are odd, then you add a -1. What is the main change is that, well, the symmetry is not the trivial one. This is the main difference. And we will see this difference in a different way. Okay, we have symmetric tensor categories. The next thing is if you have categories, you want to have functors between categories. What I mean by a symmetric tensor functor, I mean a functor between two symmetric tensor categories, which is k-linear. So all the things about all the homes are vector spaces, and I want to keep the k-linearity, let me say, in a short way. We want monoidal, so in some sense, we want to preserve the tensor product. We need some compatibility. It's not just the functor applying a tensor product is equal to the tensor product of these two objects. There is some natural transformations, as you can guess. Symmetric in the sense that it respects also the symmetry, but I want for this map to this functor to be exact, which is quite strong, but this is the meaning of symmetric tensor functors. Okay, examples of symmetric tensor factors. The forgetful functors that you can apply for representations. Every representation is a vector space plus some additional structure and you forget the additional structure. This functor is fine. As you can check that all the other properties are fine, essentially because the symmetry is just the flip, which is the same as for the vector spaces. So you respect essentially the symmetry. What happens with the super vector spaces? You can have an inclusion of vector spaces in super vector spaces, in which way? Essentially to put in the even part, but you don't have a symmetric tensor factor going from the super vector spaces to the vector spaces. Why? Essentially because you modify the symmetry. This is the thing that you can't have. You may have a monoidal, k-linear exact functor because you can forget the symmetry essentially. And you can go from super vector spaces to vector spaces, but as far as you add the symmetry, you don't have a symmetric tensor factor. Okay, so the next question is maybe when we can have a tensor factor between two categories. Why? Because the idea is essentially to find small categories D and to find a big category, fibering, this is the word that you use, fibering over D in such a way that you can reconstruct C from D. This is more or less the objective of some things about symmetric tensor categories. Okay, there is a very nice theorem by Lie from 2002, which characterizes those categories fibering over over supervector spaces. This is made over characteristic 0. Suppose that you have a Pretanakian tensor category. So I recall that this is a symmetric tensor category plus the additional assumption that the length of the objects is finite. This is equivalent to have representations of a supergroup, a fine algebraic. For those who know which is an affine algebraic group, this is more or less the same, but over supervector spaces. For those knowing Hopf algebras, this is commodius over a commutative Hopf superalgebra, which is finitely generated. I forgot to add this, but essentially this is what you have. You can reconstruct the big category from supervector spaces and a Hopf algebra there. This is essentially the way. And the last characterization is that C has moderate growth. It means that the length of the tensor powers of each object grows not so high. It means that essentially for each object there exists you can fix here a positive number such that the length is bounded by the powers of this fixed scalar. This is the main thing. And I will say just a few words about the proof because for me it's very, very nice. Essentially, the idea is that you have a symmetric tensor category, so you have an action at the level of the category of the symmetric group. And you know that you have a nice action because you have moderate growth, essentially. So the linear construct these things, the construction is so beautiful. I recommend to see this paper because for me it was quite nice. I read it during my PhD and for me it was quite meaningful. Okay, what happens when I say here that we are in characteristic 0, what happens for characteristic P? Do you have a similar characterization of some family of Pretanakian tensor categories? The answer, if you want to have, for example, moderate growth, the answer is no. You have to replace these S-vector supervector spaces. There is a nice category that I will introduce now, which is the Berlinde category, that shows that you may add this category, which is bigger in some sense than the category of supervector spaces. How to obtain this category? I need to go to semi-simplification. And for that, just a few words about semi-simple symmetric tensor categories. Semi-simple, just add that as a category, as an abelian category, let me say, it is semi-simple. Every object decomposed as the sum of simple objects. Which are the first examples of semi-simple symmetric tensor categories? Vector spaces. Every vector space is decomposed as a sum of one-dimensional vector spaces. Super vector spaces, where you have two simple objects. a one-dimensional vector space in degree 0 and a one-dimensional vector space in degree 1. These are the two simples. And what about groups? Suppose that you have a finite group. The well-known theorem by Maschke says exactly when the category of modules of gamma modules is semi-simple. As far as the characteristic of your field doesn't divide the order of your finite group. So if we are in characteristic 0, representation of a finite group, this is semi-simple, but in positive characteristic, we have problems. For example, what is the small example of where this fails? You can take the cyclic group of P elements in characteristic P. We know that this category is not semi-simple. Why? Essentially because if you want representations, the unique possible eigenvalue is 1, but as far as you have this, you can have Jordan blocks associated to this eigenvalue. So this is linear algebra that you can do in positive characteristic. And we will come back to this fact. And for many people, semi-simple categories are so important. So an old question is, how can we replace a non-semi-simple tensor category or a category in general by a semi-simple one? But I will tell you about this semi-simplification process for symmetric tensor categories. You can do this in a more general context, but I would prefer to do this in this way. Okay, what is the semi-simplification? Essentially, first we define what it is a negligible map. There is a notion of trace that you can do in the same way that as you define trace for matrices, using the dual, essentially. As you have the dual, you have an evaluation map, which is the generalization of the usual evaluation map, and a co-evaluation map, which is the way to put the one inside B tensor B dual, in the same way as you do for matrices. Essentially, what you do for vector spaces, you send one to the sum of a basis element by the corresponding element of the dual basis. And this is the way in which you represent the identity inside the endomorphism. When you look at the isomorphism between the endomorphism of B with B tensor B dual. So you have these maps for this because of this duality that you have for your category. So there is a notion of trace. If you have a map from X tensor Y and you compose with the map from Y tensor X, well, in this way that I composed, you have a map from Y to Y. And essentially, you can take the trace. And you ask for this trace to be 0 for any G, which seems quite strong. You collect all the possible negligible maps. This is a subspace of your home from X to Y. And you construct a category which have the same set, because essentially I want some set of objects, not so big category, small category. I forgot for a moment the name. And for homes, what you do is you quotient the original home space by this subspace of negligible maps. Let me say that essentially this is related with the idea to kill nilpotent elements, more or less. So you move from a nomorphism of an object X is an algebra, and you want to kill all the nilpotent elements in such a way that a nomorphism become all the nomorphisms algebras become semi-simple. This is the idea behind this process. But you do this in a general way for the whole category, let me say. Once you do this, you have a functor which sends every object to itself, every map to the map up to the negligible objects. This is the canonical way to define this functor. And you want for this functor to be monoidal. I cheat in some way because I say first what it is the functor and then what it is the structure behind it. Let me say in the quotient, because you see this C bar as a quotient. Essentially, the tensor product behind is the same as up and you move down, essentially. This is the idea. How is the symmetry? You define up and you move down. You do this, the same for every object. For example, the unit behind is the unit up, but you look at this object in the quotient. Essentially, this is what you do. And once you do this, essentially you define this C bar is a symmetric tensor category, which is in addition semi-simple. This is a
Ivan, one question.
yes.
Where I know you ended up with a symmetric tensor category because you started with a symmetric tensor category. But if you hadn't started with a symmetric tensor category, the semi-simplification works exactly the same, or are there other technical issues that could come up?
You can define semi-simplification for tensor categories with more generality. I forgot exactly the whole word where you can work, but it is more general than symmetric. For many tensor categories, you can do this. Even more, you don't need finite or many things.
Got you. Okay, thank you.
You're welcome. Okay, what happens with this functor? It satisfies all the other properties, but the exactness is not fulfilled. Why? What we are doing now, down, I will say up and down because essentially I see this as a quotient. This is the idea that I will say C is up, C bar is down. Essentially, as we are removing many maps, some which are not isomorphism up, they become an isomorphism down. Some objects which up are not zero, down they are zero. And this is the main problem for the exactness, essentially. For example, if we have an intercomposable object, we can define a notion of dimension, which is the trace of the identity, in the usual way. If this trace is zero, you can check that this object is isomorphic to zero down. So essentially, you kill these objects. We say that the set of objects down is the same as up, but essentially, in some sense, we consider many objects down which they don't exist because they become zero. This is the main idea. Indeed, as I said, this category is semi-simple, and there is a very nice characterization of the simple objects down. Up, we don't have a semi-simple category. Well, if you start with a semi-simple category and you semi-simplify, you do nothing. C bar is Z. But if up is not semi-simple, you can decompose every object as a sum of indecomposables. And this becomes simple down. But what happens if the trace here, I forgot to add the simple objects down are the decomposable ups such that the trace is not zero down. Up, well, let me say that. So down they become simple. Because those with trace zero, as I say here, they are zero. So you keep as simple objects the decomposable up such that the trace is not zero. Very nice characterization. Okay. The definition is quite technical. I will show an example, which is the example to show in this talk, which is the Berlin category. As I said, if we go back to Maschke theorem, the first problem is for the cyclic group of P elements in characteristic P. This category is not semi-simple, so you may ask what you have when you semi-simplify. I will semi-simplify the category. Here, set P means set mod PZ. Sorry, I changed the up and not down. Okay. What are the simple objects? As I said here, the indecomposable objects are the Jordan blocks of size up to P. Jordan blocks with eigenvalue 1 of size up to P because x minus or t minus 1, let me say where t is the action of the generator of set to the P, t minus 1 to the P should be the identity. So the size is up to P. Why we keep just from 1 to P minus 1? Because essentially LP is 0 in bar P. The trace is P, which in characteristic P is 0. But for all the other objects, you have trace not 0. And as usual, the unit down is the image of the unit up, which is the trivial representation. Nothing so strange. What happens is that, how is the decomposition of the tensor product of two simple objects? This is what you want to know. And this is a kind of Berliner formula. It is a truncated version. The usual Berliner formula is the addition of these objects from 1 to the minimum between I and j. But here you cut also by the minimum of p minus I, p minus j. So it means that when you are in the lower elements, 1, 2, 3, essentially the fusion rules are those for the Berliner category. But when you move up close to p, then you start to cut some object. This is the main thing. This is a way to have some idea what you mean by this. Let me show you an example, L2 times L3. The usual Berliner formula says that it is L2 plus L4. But this holds for p bigger than 3. When you do this computation in characteristic 3, what happens is that up in the representation of the cyclic group, L2 times L3 decomposes as the sum of 2L3. And this is compatible with the idea that L3 becomes 0. L2 times 0 becomes 0. It's so funny because you can do this computation so explicit. What happens here is that you start to have many scalars which are 3 or something like this. So this is essentially the option, the idea. Okay. I presented in a few slides before that this Berliner category is bad for these symmetric tensor factors. Let me show you why. If you take the subcategory, the tensor subcategory generated by L1, as usual, this is isomorphic to or equivalent to the category of vector spaces. Suppose that you take L1 and L pi minus 1. You can check that this is a category with these two objects, just these two objects. What happens with L pi p minus 1 multiplied by itself? It is isomorphic to 1 when you look at this Berliner formula. So you can check that this is isomorphic to the supervector spaces, which is so funny. So essentially, inside our Berliner category, we have the supervector spaces. There is an extra subcategory which is made by the objects labeled with the odd elements. Why? Because the Berliner formula keeps the odd elements between them. But what happens is that there is no symmetric tensor factor from Berliner P to Beck P, or even to supervector spaces. I will show you in verb 5 why this happens. Suppose that you have a symmetric tensor factor from verb 5 to super or vector spaces. The proof is the same. Take X as the image of FL3. If you look at the Berliner formula, it says that L3 times L3 decomposes as L3 plus the identity, the 1, let me say. So when we apply the tensor factor, it means that this vector space times itself decomposes as itself plus the field. But in terms of the dimension, it means that the dimension of X to the square is dimension of X plus 1. The gold ratio we have promised. So this doesn't happen. So we want to have a replacement of the linear theorem. And yes, there is a replacement. The first replacement is that we consider tensor factors, symmetric tensor factors from our Pretanakan category to ver P. And there is an extra change that you have to add to the moderate growth, an extra condition, which is to be Frobenius exact. I'm not going to say so much, but there is some Frobenius factor that you can define as the usual Frobenius map related with a field of positive characteristic. And you ask for this factor to be exact. And once you do this, this is close to the previous slide. As far as you have a symmetric tensor factor from C to ver P, you can check that your category is the category of representations of an affine algebraic group in ver P. Something that it means. I'm not going to say exactly what it is, but I will say something which is related with this affine algebraic group inter P in order to motivate my talk. Okay. For this, I need an extra part, which is how to define Lie algebras in symmetric tensor categories. You can do in the mimicking what you do for vector spaces, essentially. You take an object, a Lie algebra is an object such that you have a bracket from G times G to itself, which is anti-symmetric. It means that as far as you compose with the symmetry that you have, it is minus the symmetry. And you have the Jacobi identity plus some extra condition, because essentially this is the definition of what Ettinghoff called operatic Lie algebra. And you need an extra condition to have a real Lie algebra, but I'm not going to say nothing about that part. And you can define modules in the same way. You define an action as a map from G times B to B, plus the same compatibility that you want for modules. And what happens is that as far as you have Lie algebras in a category, in a symmetric tensor category, then you have a new symmetric tensor category, which is the category of G modules. With the additional idea that you have a forgettable factor from G modules to Z. You forget the G structure. And as an example, if we take Lie algebras in the category of supervector spaces, we recover the usual notion of a Lie superalgebra. So this is, in some sense, a generalization of Lie superalgebras. Okay, what I talk about Lie algebras in a symmetric tensor category, because there is a paper by Venkatesh, which characterizes what it is an algebraic Lie group in pair P. And this is an unusual algebraic, affine algebraic group, plus a Lie algebra in the Berlin category, and a compatibility. And because of this theorem and the previous remark saying that we have this kind of forgetful factors, we are interested to study Lie algebras in pair P. The double motivation are, first, to have categories fibering over pair P, and the second is that we can have part of this data for Venkatesh's theorem. We have the Lie algebras that we have here. So we reach here to the motivation of my talk. Let's move to Lie algebras in pair P, essentially. For this, I can tell you a different construction of pair P. We can semi-simplify the category of the truncated polynomials by T to the P, which is related with the algebraic groups in characteristic P. It is not so strange, because essentially here, this is an abelian, rank 1 abelian Lie algebra, and you take the algebra functions truncated by P, the first Frobenius part. In this case, suppose that you want to study a Lie algebra in this category. What it means, as this is a category of representation, it should be a vector space. So this is a usual Lie algebra. But we need the action of K to this T, this variable T, which is made by a derivation. As T to the P should be 0, we ask for this derivation to the P to be 0. So to have a Lie algebra in this category is the same as a pair of a usual Lie algebra and a derivation. And when we semi-simplify this object, I say that the semi-simplification factor is not a tensor factor, but it is monoidal. So if you take a Lie algebra up, it moves to a Lie algebra down. And this was explored by Arun Khanna to construct some exceptional Lie superalgebras in positive characteristics, in which way he takes a Lie algebra with a derivation to the P equals 0 and moves down in such a way that the image is inside the supervector spaces. When we saw this paper, we wanted with Julia and Guillermo to understand what happens there. And we said, well, but what happens if the image is not inside the supervector spaces? You can do the same and you can obtain a real, let me say, in the sense that it is not a previously known Lie algebra in the Berlin category. And essentially, he constructed many exceptional Lie algebras starting from Kac-Moody algebras. So I will say a bit what it is a Kac-Moody algebra. Probably many of you know what it is. This is a construction made where you start with a matrix and you want to construct a Lie algebra with a triangular decomposition. Some positive part, some negative part, which is essentially dual of the positive part, and some part in degree 0, where the part in degree 0 is abelian. I'm not going to say the general construction of Kac-Moody, but some of the part of this construction, let me say. And essentially, you want to have a positive part generated by some EIs, some negative part generated by some FI, and this matrix A tells you how is the action of HI on EJ, essentially. And for the FJ, you put a minus because essentially it is the dual part. And you have a way to relate something in degree 1, something in degree 1 should be to degree 0. So it should be something in your abelian subalgebra. This is the way in which I want to explain what it is the Kac-Moody construction. And what happens for this algebra is that if you have another Lie algebra with these 3 properties, essentially it projects on your G8. Why? Because G8 is defined as some kind of maximal quotient with these properties. This is some quick way to explain this. This is not so precise, but it is a way to understand these Kac-Moody algebras. And essentially what we are doing is we are mimicking what we can see for the algebra of matrices. SLN. SLN has a positive part, a negative part, the upper triangular matrices, the down triangular matrix, and the diagonal part. This is what we are mimicking here. And probably you know that over the complex numbers, every semi-simple Lie algebra is of this shape. You can construct essentially Kac-Moody started with this construction in a way to construct some efficient way to construct all the semi-simple Lie algebras. You can extend this construction to Lie superalgebras. Indeed, Kat made it. You can extend even to positive characteristic to construct Lie algebras or Lie superalgebras in positive characteristic. For Lie superalgebras, what you do is you choose a parity for these generators EIs, and the FI have the same parity because they are the dual. This is essentially the way to construct Lie superalgebras with this thing. What is the main problem? That for Lie superalgebras or in positive characteristic, not every Lie algebra or Lie superalgebra is a Kac-Moody one, a simple, let me say. But at least you construct many algebras in this way. For these contragredient Lie algebras, what you can see is that you have a refinement of the degree that I put behind. Behind I put the degree over Z, but you have a degree by Z to the theta. In which way? You put the EIs in degree alpha I, where alpha I is the ith vector with the 1 in the ith position and 0 everywhere. The Fi, as it is the dual, you put in the opposite one, and the Hi in 0. Essentially, this is the way in which you put a gradient. So the positive part contains all the things with positive degrees. The negative part with all the coordinates are negative, and you have the 0, which is the H. And I put here delta plus, which is the set of positive roots. Essentially, what I keep here are all the degrees with non-trivial components, which are the ones that are important for me. And here, the negative ones, which we can check that they are minus the other because it is the dual. So you have a root system, what is called a root system. And the Bae group is some group which what you can see is that it takes every component of degree alpha to degree some of the simple roots alpha I. You can check that you have this. And when you are in positive characteristic and a contragredient Lie algebra, what you can take is that by the previous remark, essentially, to take the adjoint action of E alpha is the same as to take the adjoint action of EI up to an isomorphism. So you can fix the adjoint action of EI. And this is a derivation. You can check that this is a derivation such that to the P is 0. Why? Essentially because once you apply p times this identity, you will have the p binomial numbers. So essentially they are 0 up to the extremes. This is essentially the idea. So we say with Julia and Guillermo that you can semi-simplify things starting from this point. So what we are going to take is a contragredient Lie algebra. We take as derivation the adjoint action of some of the EIs with a technical condition, which is that you have a 2 in the diagonal, which is not so strong. Because there are very few cases where you can have AII equal to 0. Essentially, this is the thing. And in this case, you can describe very nice the semi-simplification. You have again a triangular decomposition with a positive, a negative part, where the degrees are minus the degrees in the positive part, and some part in degree 0. What is this? This delta bar, what you do is you take the initial root system, and you project by annihilating the ith component. So we move from z to the theta to z to the theta minus 1. We kill the ith component. This construction is related with the construction of root system, not the classical root system, this generalization of root system. And this construction is the parabolic restriction, sometimes they call Kunz and Dedner. So essentially we have a kind of root system behind. What you have in the degree 0 part, essentially we have the image of the abelian part that we have up, but we have an extra copy of L3, which is the one with the ith component. Recall that we are semi-simplifying by the adjoint action of EI. So this is what you move to degree 0. So as far as you move EI to degree 0, the ith component is not so important. So you can understand why you project in the ith component, because it should become in some sense 0 for the degree. This G bar, you can check that this is a maximal quotient in the same sense as for contragredient Lie algebras. And in the same sense as for contragredient Lie algebras, you have a bilinear symmetric invariant form, which makes this duality that I say. The things in degree alpha are dual to the things in degree minus alpha. This bilinear form is not degenerate there. And it is degenerate as far as you consider other degrees. This is the idea. Let me show you the example of T2, because it is quite nice what you have for T2. What is the set of positive roots? Alpha 1, 3 alpha 1 plus alpha 2, 2 alpha 1 plus alpha 2, 2, and 3 alpha 1 plus 2 alpha 2, and alpha 2 I forgot to say. Okay, let's do the same simplification by 1. So what you have to do is you have to forget the degree of alpha 1. So we have a copy of L4 in degree alpha 2. Why? Because this root, and these other two roots, they are the same as far as you forget the alpha 1s. So you have 4 things in degree alpha 2 or minus alpha 2. So we have an L4 there. But you also have, because of this root, something in degree 2 alpha 2. What is this? It's a copy of L1, because you have only one root such that the component in the direction of alpha 2 is 2. This is the idea. My daughter is here. And what happens with I2? Here, what we are going to do is to forget the things in degree alpha 2. So in degree alpha 2, we have 2 things, alpha 1 and alpha 1 plus alpha 2. Sorry, here's an alpha 1. Another mistake here. Sorry. In degree 2 alpha 1, you have only one thing, because you have only one root with 2 alpha 1 plus something. And here you have something in 3 alpha 1, because you have 2 roots which are of the shape 3 alpha 1 plus something. So it is quite interesting because you have something in degree 0, in degree alpha 1, 2 alpha 1, 3 alpha 1, and the same down. Maybe if you come from root systems in Lie algebras over the complex numbers, you say, well, but you repeat roots. This is not the usual thing. But as far as you move to Lie superalgebras, yes, sometimes you have the W of some degrees. And here you can have the W or the triple of some roots. This is the same idea. Okay, when we saw the previous, let me go back to this slide, that we have some maximal quotient, some bilinear form, and so on, we said, okay, maybe there is a notion of contragredient Lie algebra or Kac-Moody algebra, let me say, in per P. And the surprise that was that we can define a bit more general for symmetric tensor categories. What is the idea is that you can fix a Lie algebra X, which is the replacement of the things in degree 0. Then you fix what you want, what you are going to put in degree 1, the EIs, let me say. And this is a module because essentially the matrix A for the contragredient Lie algebra, essentially what it fixes is the way in which your abelian algebra acts on the positive part. And I told you that the category of modules over X is a symmetric tensor category. So you have duals, you have tensor products, and so on. So you are able to construct the dual between other things. So you may ask to have a map D from B tensor B dual, which is an X module, to X itself, which is again an X module with the chain action, and to ask for this map to be a map of X modules. What is this map BD? Essentially, this map D, I'm going to move to this part. This map D is the replacement of the EI Fj is equal to delta Hi, let me say. This is the way to define the bracket between the things in degree 1 and the degree -1 to go to degree 0. This is the map D. What we can prove is that there exists a contragredient Lie algebra, which is a set-graded Lie algebra in the category, with the representation in degree 1, the dual in degree -1, the X in degree 0. As I said, the image of D is a way to control the bracket between degree 1 and -1 going to degree 0. So there is some kind of free Lie algebra that you can define between B and B dual. There is a notion of semi-direct product, which is the extension of the usual semi-direct product. And you mod out by the idea that the bracket between the degree 1 and degree -1 goes to degree 0 through D. This is more or less the idea. And this quotient is maximal with the properties above. So that's the idea why we call this a contragredient Lie algebra. The other funny thing is that suppose that your X module V decomposes as a sum of some VIs, which are X modules too. Then, as for Lie algebras, the usual Lie algebras, contragredient Lie algebras, this contragredient Lie algebra is set to the theta gradient with every VI in degree alpha I and the X in degree 0. And again, you have a bilinear symmetric invariant form in this contragredient Lie algebra with the same properties. A duality between degree alpha and degree -1 alpha, and they are orthogonal otherwise. Essentially, this is the idea. For us, a surprise was that for this X that we have here, we don't act so much. I don't put, there are some conditions that should be here, let me say. But it is not, for example, that it should be abelian or something like this. And when I went to a conference last January, I was talking with Alex Sherman, and he asked me some things about that. And the surprise was that those days we put this paper on Archive, and he put this paper a bit before about the construction of the queer Lie algebras as Kac-Moody algebras, but the modification was that they put something which is not a torus, a usual abelian Lie algebra in degree 0. And this was the same idea that we had. Essentially, we put in degree 0 something that could be non-abelian. So essentially, our construction generalize what they do there. So you can recover the queer Lie superalgebras as contragredient Lie algebras in the category of supervector spaces. This is one of the ideas. But let me show you some other examples. Venkatesh, the same as I mentioned before, defined the idea of GL of an object in ver P. Essentially, what you do for GL, this is the algebra of matrices over a vector space. What that you can see here is tensor product again, sorry. This is the tensor product of P with B dual in such a way that when you multiply, you apply the evaluation in the middle. This is an associative algebra. And as you have for Lie algebras over any field, let me say, if you have an associative algebra, you can construct the corresponding Lie algebra. This is the way in which you construct GL of W. As you have a trace map, you have the same idea to have the kernel of the trace map. And this is the definition of SL of W. Suppose that your element W decomposes the sum of some L and I. Well, when you fix this decomposition, we can find a way to show that this GL and this SL, they are contragredient. So these classical objects, they are contragredient. In which way? We take as X the diagonal. It means the tensor product between L and I and its dual. And you take as X L and I times L and I plus 1. The first diagonal over the main diagonal, let me say. And for the dual, you go down. Essentially, you have the same ideas for SLN. The contragredient Lie algebras that we defined before as a semi-simplification of the contragredient Lie algebras, they are also contragredient over ver P. And we have more examples that I don't want to explain here, but in the paper, we have some extra examples that we can construct with these contragredient Lie algebras. So the main idea is try to obtain the classification of contragredient Lie algebras, at least in ver P, let me say. What it is the tool that we expect to obtain is a kind of root system. Because motivated by this last part, that you have a set to the theta gradient, the idea is that you can define, again, a kind of root system for these contragredient Lie algebras. Let me say you something. Here, this Lie algebra is not really in Z. It is in the int category. Why? Because essentially it is the direct sum of infinite objects, not finite objects. And so when I say we want to classify contragredient Lie algebras in the category, it means that not in the int category, really in the category. So it means that we start with an infinite object and we want to quotient quite a lot in order to have something which is finite. But it's the same as you do for Kac-Moody algebras, essentially. Okay, that's all. Thank you so much.
Thank you so much, Iván. Let me stop the recording. Thank you very much.